Now that we have the Pauli principle, we can now, at least in theory, we can position the electrons in any atom, in any element, depending on the number of electrons or the atomic number Z. The idea is very simple. We start by putting the first electron in the lowest energy state, which is the 1s state, and then we put another electron in the same orbital, just give it an opposite spin, so as not to violate the Pauli principle. And if there's a third electron, then we have to put it in the next highest orbital because we don't want to violate the Pauli principle, and so on and so forth until all the electrons are filled. That's the idea. So what we need to do then is to figure out which state is the lowest energy state, which is the second lowest energy state, which is the third lowest, and so on and so forth. This may not be all that easy because when you consider a multi-electron system, you must consider not only the energy of the orbital itself, which involves the interaction of the electron and the nucleus. You must also consider the electronic interaction, that is, different electrons in the same atom can repel each other depending on, and the strength of the repelling force depends on where they are. If they are closer, the repelling force is greater, they will have greater Coulomb potential, which is positive, and that will raise the energy of the system. That's not desirable, and so on and so forth. So it's a complicated issue in general because of the multi-electronic interaction. For that reason, the only atom, the only element whose electronic behavior is totally understood is hydrogen, because there is no issue of electron-electron interaction within the hydrogen atom. It's got only one electron. The next one up, helium. It sounds like the next simplest atom, right? No, it is not. First of all, we have not solved the Schrödinger's equation for the two-electron helium system. We have not done that yet. Nobody has ever achieved that. For helium and any other higher Z number particles, higher Z number elements, we can only approximately understand what's going on to find the approximate energy levels and so on. We have not had any exact solution except for hydrogen, because the multi-electron system, the Schrödinger's equation, is pretty much impossible to solve if you want to know the exact solution. But we know some pretty good idea how to position these electrons. We can do an approximate calculation of which energy level is the lowest, which was the second lowest, and so on and so forth. So we know at least how to position these electrons. And again, the last 1, 2, or 3 electrons are the most important because those are the ones that will change their orbitals upon chemically interacting with other atoms. So those are the ones that will determine the chemical property, valence electrons. Okay, now, here we look at how the energy levels are labeled. N equal to 1. This N is the principal quantum number. Different N, we call it different shells. Okay, different shells. And N equal to 1, 2, 3, the different shells. And within each shell, there are the same N, there are different L numbers. These are called subshells. And L can go from 0 all the way to N minus 1. So for N equal to 1, L can only be 0. And for N equal to 2, L can be 0 and 1. For N equal to 3, can be 0, 1, 2, and 0, 1, and 2. Now, we saw that before, right? We know that. But within the same N and L, you can have different orbital magnetic quantum numbers ML, which we called M before. This can range between negative L to positive L. There are 2L plus 1 such values for the same L. So therefore, you have different orbitals for the same N and L. For L equal to 0, M can only be equal to 0. But for L equal to 1, you're going to have 3 different values for M, which is negative 1, 0, and positive 1. You see here, and so on. So each quantum state with the same N, L, and ML is called an orbital. Within the same orbital, how many electrons can put in? Well, they have already the same N and same L and same ML. The only thing that can vary is the spin. Spin up or spin down. These are only 2 possibilities, okay? And therefore, we can put 2 electrons within the same orbital without violating the Pauli principle, because their spin quantum number along the z direction is different. And we have done a calculation as to how many different orbitals or how many distinct values of L and ML there can be for a given number n. Okay, and the formula we found, that was I believe the second lecture of this chapter, was n squared. Okay, n squared is the sum of this 2l plus 1. That's the number of m's, l going from 0 to n minus 1, all the possible values of l. So you're summing over all the possible values m and all the possible values l, you get n squared. That is the number of orbitals available for a given shell of given n. Now, how many particles, how many electrons can we put to fill the entire shell? That is 2n squared. Why is that? Because, again, for each orbital, I can put 2 electrons in there, one spin up, one spin down. So that is the total number of electrons I can possibly fill for that shell. For n equal to 1, 2n squared equals 2, so I have 2 particles, okay? 2 electrons, that's spin up and spin down both in 1s. For n equal to 2, we go to 2 times 2 squared, and that's 8. So we can put 8 electrons in n equal to 2, and so on. So let's see here. We already know the simplest case, which is hydrogen. That's only 1s, and the helium is also very simple: 1s spin up and 1s spin down. This is the next one up. Lithium. It's got 3 electrons. 2 of them will be in a 1s state. Okay, all these are 1s states. This is what n equal to 1 can do for you. It only gives you space for 2 electrons. And n equal to 2, you can have up to 8 electrons. Up to 8 electrons. Lithium only needs an extra electron there. This is the next one up, next one up, next one up, and so on. So you have, for n equal to 2, you have 2s and 2p. Here is only 1 electron, 2, 3, 4, 5, 6, 7, and 8. This element, neon, has 2 electrons in n equal to 1 and 8 electrons in n equal to 2. So it fully occupies everything available in the n equal to 2 state, or n equal to 2 shell. And we can write down the electronic configuration starting from this guy here, 1s2. 1s means the orbital is 1s, and there are 2 of them. Okay, 2 of them, so that 2 means there are 2 electrons. And then 2s, this is 2s state. There is only 1 electron there, so it's 2s1. That's for lithium. And this one, beryllium, 1s2. So there are 2 particles, 2 electrons in the 1s state. 2s2, 2 particles, 2 electrons in the 2s state, and so on. And next one has a 2p1. Boron has a 2p1. Carbon has a 2p2, and so on and so forth. This is how you write down the electronic configuration, just as you would do in chemistry. So that's how we determine the electronic configuration, which in turn determines the chemical property. Now, there is an important rule called Hund's rule, which determines how we position particles, electrons, within the same shell, within the same n. Now, 2s, looks like you first fill up 2s, and then you go to 2p, right? Look, then you fill up 2p. And within 2p, what you want to do is you want to spread out these electrons and have the same spin. Look at that. So the total spin is maximized. Total spin is maximized. Okay? So here you have, in this case, you have 4 electrons in a 2p state. So this guy is forced to share orbital with another electron of the opposite spin, and so on. This is when everything is filled. Where does Hund's rule come from? Again, Hund's rule says you must, if you have, say, several electrons that can occupy 2p, what you want to do is if possible, you want to spread these electrons out in different 2p orbitals to have the same spin, so that you maximize the spin, the total spin. Where does Hund's rule come from? Hund's rule is an empirical rule which can be understood qualitatively from the idea of the anti-symmetry nature of the wave function of the electron, plus the principle of minimization of energy. We want to minimize the energy of the system, and the particle, the atom is very clever. It positions the electron in such a way that the total energy is minimized. That's what it wants. Okay. Now we know that electrons are fermions, so their total, if you have a wave function involving 2 electrons in the same atom, The wave function must be anti-symmetrical under exchange. But in this case, we must also consider the electronic spin. The electrons have spin. They also move in space, so the wave function for the two electrons is the product of two parts, its spin part and its space part. These are unrelated, the spin part and space part, therefore just the product of the two. Now, the overall wave function must be anti-symmetrical, which means there are only two possibilities. If the spin part is symmetrical under exchange, the space part must be anti-symmetrical under exchange, and vice versa. If the space part is symmetrical under exchange, the spin part must be anti-symmetrical. What Hund's rule wants is to make sure that, if possible, the electrons will have the same spin. So if the same spin, when you exchange the spin of when you exchange these particles, you get the same spin, right? So therefore, it is symmetrical. The spin part is symmetrical. That's what Hund's rule wants. Why is this a good idea? Because if the spin part is symmetrical, what does that lead to the space part? It must be what? Anti-symmetrical, right? Anti-symmetrical means the particles want to avoid each other. Anti-symmetrical. So, see, anti-symmetrical is like it's like an odd function. An odd function is zero in the middle. So you have a wave function that looks like that. It's zero in the middle. Okay. If it's a symmetrical wave function that looks like that, it's not zero in the middle. So that means the particles, being anti-symmetrical in space, they are positioned in such a way that they try to avoid each other as much as they can, while occupying different quantum state, different levels. Different orbitals. That's also important because different orbitals are positioned a little bit further away from each other. So the whole idea is the electrons will be in such a space configuration that they try to avoid each other as much as they can, therefore reducing the positive Coulomb repulsive potential energy. Make sense? If, on the other hand, if this guy were to made to be anti-symmetrical, so we got one up and the other down, then the space part is symmetrical, then the particles' wave function will be closer to each other, and therefore there will be more repulsion, which will raise the energy of the entire system. So that's what Hund's rule really says. By maximizing the spin, you are actually trying to minimize the repulsive potential energy between electrons, therefore reducing the overall energy of the atom, which is what the atom wants. Another thing I want to talk about is the periodicity of the chemical behavior. Neon, just like helium, belongs to what's called noble gas. They don't want to have anything to do with any other elements, so they do not engage in chemical reaction. Even they don't want to deal with each other, therefore all the neon and helium, they're all gases. They're what's called noble gases with single atoms per molecule. They're monatomic molecules. And there's a good reason for that, because all their shells are filled up to n equal to 2 for neon and n equal to 1 for helium. They do not want anybody else here because it's all filled up. Otherwise, you violate the Pauli principle. You cannot introduce a third electron there. And they certainly do not want another electron. Let's say helium certainly do not want a third electron, because that third electron would occupy a high energy state. Why does it want to do that? Okay, so therefore, it's chemically inert. So all these elements with completely filled shells and no partially filled shells are considered chemically inert. They do not attract or repel each other or anybody else. They just want to be left alone. So they only exist in monatomic gaseous state. These are noble gases. On the other hand, lithium has one extra electron compared with a completely filled shell, and this electron has considerably higher energy than these two electrons. Therefore, it's loosely bound. It's very loosely bound to the parent atom. In a chemical reaction, this 2s electron is easily lost. If somebody else wants it, it's easily lost. Therefore, lithium is an active metal. A metal in chemistry, we call it a metal because it can easily lose electrons. And lithium is a very active, very strong metal, which means it can easily lose that electron. And so on. So as you go from completely filled shell, in the case of helium, going and add more electron, all the way till to neon, you have one period. You have one period in the behavior of these elements. They go from inert gas to very strong, and then you start with very strong metals, and then very strong non-metals, such as in the case of fluoride, because this guy has one extra electron that it would need to fill the complete shell, and once it fills that shell, the energy is still keep very low because you do not have to push yourself up to a higher energy level of n equal to 3. Therefore, it doesn't mind getting another electron there, so it is very eager to get that electron. That makes it a very strong non-metal. And once you have that extra electron, the mission is fulfilled. You become a neon, and chemically you have just enough number of electrons to fill the entire shell. So again, you become chemically inert. So from one noble gas element to the next noble gas element, you go through that cycle from very strong metal to very strong non-metal. And the cycle repeats itself as you go beyond neon. You add one more electron, and then that electron is just like this electron here. It's not very welcomed by the parent atom. The atom is easily going to lose it. Again, you get a strong metal, and that, as you know, number 11 is sodium. So you get this periodic behavior, chemical behavior. That is the physical reason behind the entire periodic table. We can visualize this by this plot of ionization energy. What is ionization energy? It is the energy needed to pull an electron out of a complete atom. Okay? If this energy is high, that means it takes a lot of energy to pull the electron out of the atom, which means it's tightly bound to that atom. Therefore, the electron is not easy to get pulled out. So that means it is not a metal. Okay, because in a metal, the electron could, at least that electron, the first couple of electrons could easily be pulled out. So it's difficult to pull the electron out. As you can see here, this ionization energy plot as a function of atomic number z is sort of a periodic behavior. It goes down, up, and so on. And the peaks at these cases, helium, neon, argon, krypton, and so on, all these are what? Inert gases. All these are noble gases because they have completely filled shells, and therefore it is very difficult to pull that electron out. All electrons are tightly bound to the parent atom. It's difficult to pull it out. And then right after that, right after each of these, you have a very low value of ionization energy. This is where the electron can easily, this one electron can be easily pulled out. Lithium, sodium, and so on. These guys, potassium, okay, this is potassium. These guys are very strong metals because they have one extra electron beyond a completely filled shell. This electron is loosely bound to the atom, and it doesn't take much effort to pull it at all. So these are good metals. Okay, cesium, in fact, is the strongest of all metals in terms of its ability to chemically react with nonmetals. So you have this periodic behavior, and for that, because of that, it is possible to construct a periodic table including all the elements. The periodic table, as you know, the greatest discovery in the science of chemistry was the brainchild of the famed Russian chemist Mendeleev. And here is the famous periodic table. I'm sure you have seen it from your chemistry class. The periodic table, on the periodic table, this side, strong metals, with the exception of hydrogen. This side, this last column, group 0, these are noble gases. Okay, they are the ones that are chemically happy. They don't need anybody else, or they don't want to lose any electron. They're just happy by themselves, completely filled shells. These are very strong nonmetals, alkaline group, and as you move this way, the tendency to lose electron becomes stronger and stronger and stronger. And you lose that way, you go that way, the tendency to lose electron get weaker and weaker and weaker. So we have very strong metals going to very strong nonmetals. All these things in between are called transition metals. They're still metallic, but they're not as eager to lose their electrons as the first group. And somewhere between metals and nonmetals, we have several important elements. These are semiconductors. Metals are conductors, right? Nonmetals are not conductors in general, in elemental form at least. But somewhere in between, you have semiconductor. They're somewhere in between metal and non-metal. Silicon being the most famous example. And then we have carbon. Carbon is is classified as a non-metal, but it's not that far from metals. Aluminum, for example, is a metal. Because of its position in the periodic table, carbon is an extremely versatile element. It can engage in all kinds of chemical reactions, and therefore, there is a reason why the life on this planet is carbon-based because of the versatility of the carbon atom. In fact, in the next chapter, we're going to look at what kind of elemental forms we can think of for carbons. There are different ways for carbon to exist as an element. It's more complicated, more colorful than any other element. So we have a whole bunch of metals here. These are transition metals. So this is the periodic table. Again, hydrogen is the odd one out. Supposedly, everything here, you have the tendency to lose that electron easily. But hydrogen is not a metal because it's got only one electron. There is no other electron nearby to provide any repulsion, which is a tendency to push that electron out. It only experiences the force from the bare proton, right? So it is not easy for the hydrogen to lose that electron. It is the only non-metal on this side of the periodic table, and it indeed is the odd one out. It behaves differently from anything else on this side. All right, we're not going to get very deep into the periodic table because the calculation involving how to position these orbitals, that is the real quantum chemistry. It's not something that we can do in 1D, but at least we have the idea why there is such a periodicity. What we can do, though, is to look at the optical behavior of medium-sized atoms. Medium-sized atoms. We're not talking about hydrogen anymore. So something here around like Z equal to 40 and 50-ish. And these are atoms with relatively deeper electronic orbitals. Deeper means they have lower energy because they have a relatively large number Z here, so they get more attraction from the protons, so that makes the total energy lower or deeper. And what we do is we study what's called X-ray spectra of intermediate-sized atoms. They're mostly metal.